So this is the Particles Homework Booklet question 6. We're asked first of all to complete the following equation to describe the decay of potassium 40 by beta minus. So we start with the potassium 40 nucleons, 19 protons. Beta minus is where you need to go next, and the point about the beta minus is that's 0 minus 1. We've got a neutron turning to a proton, so the total number of nucleons doesn't change. The number of protons goes up by 1, so to make the equation balance we represent that as 0 minus 1 beta minus. To make that balance then we've got 40 nucleons to start with. We must remain at 40 nucleons, and we've got 19 nucleons to start with. We must remain at 19 nucleons, so the calcium must be 40-20 calcium. And then we've got to remember the electron antineutrino. And the electron antineutrino has no nucleons, no protons, and doesn't affect those numbers, so is simply 0, as that's given there. When a sample of potassium 40 decays, the emitted beta minus particles have a range of energies from almost 0 up to that maximum value, Emax. There's that maximum value, and the spectrum of energies observed is shown in the figure below. So this is about the number of particles, and that's the energy. So we get a significant number of beta minus particles, very low energies, rises up to a peak at that energy there, and then drops down until we get a very small number, or smaller and smaller numbers as we approach the maximum kinetic energy. What we're asked to do is to explain how this evidence led Pauli to predict the existence of a previously unidentified particle. So the starting point of this is that we always get the same energy released in a decay. We see that with alpha particles. The alpha particles all have the same amount of energy. They all bring that energy from the alpha decay. The beta particles will do the same. And what's crucial is that the total energy of the beta and the recoil nucleus, so that's the beta particles coming out of a nucleus, and the total energy of that beta and the recoil nucleus isn't constant. In other words, there is missing energy, and therefore there must be another particle to carry away that missing energy. In fact, ideas we'll be approaching during the second term about momentum shows us that we can't, that if we had only two particles, only the beta and the recoil nucleus, they'd always take the same share of energy. So the fact that the beta is going away with different amounts of energy must be telling us that we've got another particle there each time. So that's the Particles Homework Booklet question 6.